One of the most interesting announcements I came across there was Spanner Omni, because Spanner is this very, as I understand, this very highly optimized database. And it was highly optimized really for Google infrastructure. You took Spanner in another direction, so I'd love to have you talk about that.
You're listening to It's About Data, episode 74. Our guest today is Sailesh Krishnamurthy, VP of Engineering for Operational Databases at Google. All right, Sailesh, welcome. It's great to have you here today to record post GCP Next.
Yeah, we're just trying to catch up here. Sailesh, you're Vice President of Engineering for Operational Databases, and there was really quite a slew of announcements that came down, at Next in Vegas. That was like 6 weeks ago. God, time just was so fast. But anyway, Sailesh, before we dive into that, can you give us a little bit, just tell the audience a little bit about your background and where you're coming from?
Sure. Thank you so much, Tony and Martin. Thank you for joining us in Vegas. I think you're right. We had a whole slew of announcements, and it was fun to engage with all of you. So I've been in the database business for the last 28 years, so almost my entire working career. I worked in IBM in the mid-90s on DB2, did a bunch of different things. Past then, worked on streaming databases. I was at AWS prior to coming to Google, where I was general manager for Aurora and managed MySQL databases, and I've been at Google for almost the last 7 years now.
Right. And basically, what was really interesting, what came down was that we started to, one of the most interesting announcements I came across there was Spanner Omni, because Spanner is this very, as I understand, this very highly optimized database, and it was highly optimized really for Google infrastructure. It was a very unique creature. Now we're starting to see a lot of folks basically try and replicate that in their own ways, but you took Spanner in another direction, so I'd love to have you talk about that.
Yes, I think first, Spanner has been transformational for Google, right? It's at the heart of almost all our critical systems inside Google, whether it's ads or Gemini or search, and through the years there have been more and more uses. When we took it to cloud, we use the same infrastructure. So there's the same Spanner infrastructure that powers inside Google. That's part of our cloud customers. And the last couple of years has been quite transformative for Spanner's growth. We've seen, for a bunch of different reasons, for AI, because we really push the multi-model story for Spanner. We have things like graph, full text search, and vector search. It's all come together at the right time. And at the same time, I think there are a few trends that we see in the industry. One is, the truth is, customers are on more complex infrastructure footprints. It's not that just only on one cloud. So they use multiple cloud vendors. Many of them run their own data centers, especially with ongoing challenges in getting availability of whether it is TPUs or GPUs or compute or storage. People are spreading their infrastructure around. And then as a result of that, there are a lot of customers who will come to us and say, hey, we'd love to use Spanner. We want to be close to Google Cloud, but we also want to have this service available in other environments. Sometimes it's coming from a stress exit thinking, right? It's almost, in theory, if something really bad happens, what is our option? Sometimes it's because they want a DR scenario. They want to take the Cloud Spanner database, and they want to have, for business continuity, the data replicated to some kind of an on-premises environment. And in some situations, it's they are running something really complex on multiple different clouds, and they want to they really love Spanner. They realize there are many challenges with just commodity open source databases that really can't easily be solved. And so they want the power of Spanner, but they want it available in multiple regions. And so we've known about this for quite a few years. People have been coming and asking us. Sometimes it's inhibited their decision to use Spanner, right? It kind of stops them from using Cloud Spanner because they worry about what are these other scenarios. And so about a couple of years back, we decided we'd really push hard on this. And there are many, many hard technical problems to be solved, because if you think about a service like Cloud Spanner, as you put it, it's optimized for Google scale. It's optimized to run on our infrastructure. But it's also a fairly complex system in the sense that it's not just Here's a binary that you go run somewhere. We have a whole bunch of different services that are all running behind the covers, orchestrating this amazing user experience. So we had to solve many fundamental problems. We had to solve engineering problems in terms of core infrastructure components that we get inside Google, true time, storage systems like Colossus, and to find a way to run them outside. We had to solve packaging problems in terms of, okay, now if I don't have just these magical API endpoints in the cloud, how will a customer organize and run this? We don't want to have the customer to run the same set of services that we are running. And so how can we package it so that they can more easily run it? And in our own systems and teams, we have to think through many different aspects of commercial considerations and what makes sense. So it's a complex set of things. We're very excited that we announced it. The reception and interest is really great. We are very excited to see this go to the next step.
So let me follow up on true time and commodity hardware, because famously Google put out all these blog posts about basically how to beat the cap theorem using very precisely synchronized clocks, right? And that's also using very specific Google hardware. How do you deal with the fact that you have all this different hardware running notoriously different clock systems and still get that kind of performance?
So it turns out, there's a lot of details, right?
Yeah,
and I think the best possible performance,
yeah.
best possible experience will still be in the cloud, especially when you're running very complex, globally consistent configurations and things like that. But Spanner is more than just true time. It also provides this amazing scale-out architecture. And so we've built something we call software-based true time that in many situations that we think customers will have, this will provide a very good user experience. There will be some corner cases where it will not be ideal. And so we will work through them as we get to them. We've even had customers come and say, hey, what if we had some kind of the same hardware that you guys, or we think you guys have in your data centers, and we put it, will that work? And so our answer to all of this is sure, we'll look at what you have, and we'll find a way to work with you.
Got it.
I think what's really interesting about this is that when Spanner really debuted, and again, when I say it debuted, it's kind of a false term, because basically Google had been using this internally for at least like 15 years, something like that, plus or minus. I mean, a long time. It wasn't a new database, but that when you basically released it, as a commercial offering on your cloud, at the time we looked at this as being, this is kind of a freak. I mean, we've talked about active databases, but more in the realm of the theoretical, like, is this really, feasible in the physical world? And yet, what we found in the last few years is virtually everybody has come up with their own. I mean, yes, originally you basically had some folks over at Cockroach and Yugabyte tried to do there's actually surprisingly Cockroach has had some recent success on this, but that might actually be to my point. So you've seen the others. You've seen basically AWS. You've seen Oracle. All join in on this, and so something must be happening. So I want to look not so much at the technical side, but why is this happening? What's out there in the customer base that's really demanded, this type of basically very distributed transaction database, as opposed to, let's say, your traditional, say, primary, secondary?
I think a few things are going on. I'll try to draw two broad claims. I'm not sure if it explains everything, but at least I think two things I see. One, consumer-facing applications, the kind of scale that demands are growing. There's more and more of these services on, and solving, I think, the core problems. I mean, there are many different things that Spanner gave. Spanner provided consistent replication across data centers, but Spanner also provided the ability, even if you didn't go across data centers, even if you are even only in a single region, Spanner provided the ability to transactionally shard your systems and scale out, which I think is an incredibly common usage pattern that a lot of new people need. Irrespective of whether you wanted global consistency and all of that piece of infrastructure. So one theme is, in general, the explosion of large-scale consumer workloads and so on. And so we see this even amongst our current Spanner customers, people who build frontier AI models, people who I like to call them token purveyors as opposed to token consumers. And they have to store a lot of data at a lot of scale in a high throughput, high QPS, low latency fashion. And so for this class of customers, these are real problems. I think these are big problems. And so I think this is a trend that we're seeing. Second trend, I think, is around maybe call it SaaS workloads, people who have a very large number of smaller customers and a few very large customers, as opposed to just pure consumer workloads. I think you see a lot more of that happening too. And common to both of these kinds of use cases, you have the challenges of sharding. And so I think for all of these kinds of sharding workloads, I think Spanner has turned out to be a great solution. But then there's the other piece that traditionally, as you've been in the database business too for such a long time, a lot of the way operational databases grew was people buying applications or people migrating existing databases. So if you have an existing database that worked on a commercial database model or an open source database model, the easiest, the lowest friction path was, hey, can I just go to a similar kind of architecture? The database, logical database design, physical database design remains the same. And if it worked kind of well in that world, then it works reasonably well in this world. I think what we're seeing as perhaps the meta theme is new workloads. And I think the new workloads are getting really exciting, especially for AI-related use cases. I think there's a theme that we are seeing that where people thought you needed specialized kinds of storage. Great example for AI gamers. People thought that they needed a specific vector storage, custom vectorized vector storage system, or they thought you needed a custom graph storage system or full text storage system. And that, I think the industry went through a path where you had perhaps an explosion of these different database systems, which in my opinion led to two problems. You had one, architectural complexity, because effectively if you have all of these different systems, you are connecting data and setting up data pipelines. And this is particularly interesting from the perspective of unstructured data, which we talked about before the call. Database systems, I think historically have had, I like to say one job. Don't lose your data, provide exact results for the data. You have a query, you get exact results for the data. But in this new world, you have unstructured data and structured data coming together. And now what becomes important is not necessarily exact results, but the best quality results. It's about ranking and relevance. And now you have to combine your structured and your unstructured data. And that, I think, is a particularly interesting problem. Now, like I said, people went down this path of multiple different bespoke systems, connected through various data pipelines. And that was architectural complexity. But there was also application complexity, because now you have to combine the data from your structured database and from your unstructured database. If I can just give a simple example, if you imagine I have to combine a vector store for, let's say, storing information about item descriptions in an online retailer. We've partnered with Target.com. They use AlloyDB AI for their online catalog search. And so that is an interesting system, or classes of that kind of system, where you may be asking queries on your unstructured data. But along with asking queries about your online catalog, you're often asking predicates in the same query, maybe about price information, which is real-time information that is not perhaps in your vector database, that actually sits in your operational database. And if you have bricks and mortar stores in addition to your online store, you might want to have a predicate combining that is talking about the inventory of those items. So when I construct a search in that website, if I ask for something, I'm asking for a particular item, I want to look at based on the best semantic fit with respect to the search term I have. I want to combine something like price, and I also want to combine inventory. That is a complex query. And if I have to stitch multiple systems to the application level, the application developer has to know which system do I probe first. Do I always probe the vector index first? It could turn out I could probe my vector index first and get 20 results, and none of them satisfy my other predicates. So then what do? I have to go back to the vector index again? This is a nightmare. This is kind of the world people building applications are. Our perspective is this data can live in these different systems. The indexes can be put together in your operational database, and you can just have one query with multiple predicates. That's the path we are seeing the world go towards. And that's where having a multi-model architecture where you're able to support vector indexing, full text indexing, and graph all together in a single system is particularly exciting.
Yeah, I can tell you, I mean, from my perspective, I've done a lot of big migrations, including on big Google Cloud, and this new vector capability is so exciting because I can look back at migrations we did and say, you know, had we had that capability back then, we wouldn't have had to do an extraction from BigQuery to Spark to do this kind of calculation, say. But I actually want to dig in on another issue here, which is a crossover of business and technical and even political a bit. And that is, what are you hearing from your customers on data sovereignty, and how are you responding to that? I know you're on the database side, but I'm sure you get a lot of these queries about how do we address data sovereignty questions for American customers, for European customers. Yeah.
And especially it's really pertinent as you have a distributed database. So it seems like that would be, well set for this.
Yes.
The data sovereignty question is great. I think, one way of thinking about it is it's just how you are organizing storage systems. So certainly sovereignty, reliability, availability, these all go together, right? So in Google Cloud, we have this idea of what we think of as 3, 4, 5 reliability. If you want 3 nines, you can run that in a zonal service. If you want 4 nines, you can run it in a regional service. But if you want 5 nines, the only way we know how to run it is in a multi-regional service. Right? And I think it's a simple way to think about it. Mm-hmm. But in addition to zonal, regional and multi-regional, which are ways of looking at this from a, your footprint and looking at it in terms of nines, you have, as you point out, sovereignty requirements from a jurisdiction perspective. And so you might want to say, I want data to be stored only in a particular region. And there are, I think, multiple pieces here. So I'll tease apart 2 separate problems. One is partitioning subsets of data of users in a large database, where I want to have some number of users whose data is stored only in a given region, other sets of users whose data is stored in another region. Spanner now supports geo-partitioning, something that we have. It's in production. You can partition your data in these different ways, and at the same time, logically, from the application's perspective, it is just one single large table or collections of tables. But the data can be partitioned. We can guarantee, based on a partitioning key, we can guarantee the storage in a given geographical location. So I think that's one interesting way to go address it. But we've got another kind of problem too. And of course, there are many reasons to do this kind of partitioning. Partly it's data sovereignty, but partly also where people, you want to have affinity where workloads come in. I have these large global workloads. The user logs into Asia. They want to get their data faster. And so it's a mix of both of them. But there's this other interesting sovereignty problem that comes up where you want to keep the data within the jurisdiction, but you still want to have high availability. It's particularly important for banking customers. So there are many jurisdictions in the world where there are only a limited number of regions for each of the cloud service providers, right? So you may have 2 regions in India, for instance, I think Australia, Canada. There's a bunch of jurisdictions where people want the Holy Grail. They want 5 nines of availability, which, as I said, typically requires a multi-regional configuration. But they also want to guarantee that the data remains in jurisdiction. This is a really hard problem to solve because in most setups which try to give you that high, 5 nines of availability, they need to have at least 3 regions. And if you can only have 2 regions in a given jurisdiction, then you have an interesting challenge. So the way we've actually addressed it is we built for Spanner, and this is the Cloud Spanner, a special 2-region, multi-region architecture where we are only restricting, where we can guarantee that the user's data remains in 2 regions. And we use a 3rd region with only metadata. That is, no user information goes to the third region. The 3rd region contains what we think of as control plane information. So if I have a very large database partitioned by a bunch of different groups, each group, the data is stored in different replicas, and effectively one of the replicas is a leader, and that information for a given group, which replica is the leader, is what is stored outside in a region outside the jurisdiction. So it's a particularly interesting way to address data sovereignty, where you can combine very high availability and still guarantee that the user data remains in the jurisdiction.
Right. Well, Sailesh, I know that we've only really scratched the surface here, but actually that's really what we do. It's we're here to start the conversation, but we'd love to have you back in the future, but we keep this conversation going. But we very much appreciate you taking the time and sharing with us today, basically your insights on why basically the whole use case for Spanner is really kind of broken out.
I appreciate it. Thank you so much for your time.
Okay,
Thank you.
good talking.
Take care.